So, where we were before, all right, we started in the auditorium, we walked down to the SA100, and now we walked around to, we're in front of the clean room, we're about where the number 12 is. It's clean in there. It's a clean room. You need a clean room because when you build high sensitive, high voltage, very sensitive equipment, you don't want a lot of dirt getting onto it, because when you charge it up to 1,000,000 volts, dirt acts as a lightning rod. That's bad. So, in here, it's about 3,000 times cleaner in terms of dust per cubic foot than it is out here. If you want to go in, you got to wear the white bunny suits. You might have seen the person standing in the doorway back there. White suit. That's not to protect you from something. That's to keep your dirt from getting into the air, because you're all really filthy. No offense. We're all dirty, okay? So, suffice to say, very, very clean environment. In this room we're building right now, if you can look in there, there is a cylinder, a vertical metal cylinder with a hole at the bottom. Everybody try to get a look. It's right, it's behind the stool, That vertical metal cylinder is made of almost pure niobium, meaning it's all superconducting metal. Therefore, when you cool that thing down with liquid helium, you can charge it up to 1,000,000 volts lickety-split. And the hole at the bottom basically is to emit a beam of nuclei. Nuclei come in one side, you charge to 1,000,000 volts, shoots the nucleus out the other side. You put a bunch of those cylinders in a row, you have a linear accelerator. Ladies and gentlemen, that is the next generation of nuclear accelerators. We invented it. We made that design up ourselves. We are building the first ones in the world. They're going in a line up here on this shelf. Actually, in that green box, there's 6 of them right now. There's room for another box. Ultimately, we'll have 16 of them in a row. And that linear accelerator will be able to make nuclei go about 8% of the speed of light. 8%? We were doing half the speed of light before with the cyclotrons. Who cares about 8%? That's how fast nuclei go in a star. You want to study nuclei in a star? This is cheaper than going there. You recreate nuclei under similar conditions, and then you can study them. That's what this thing is for. In fact, when it's done, maybe this year, we'll be the only place on the planet that can do this kind of experiment, and we'll be number 1 in the world for nuclear astrophysics experiments. When you want to be number 1, being the only one is really good. Trust me on that. This is actually a really nice new kind of accelerator, but this is actually practice to some extent. The FRIB accelerator I told you about is 400 yards long, and it's going to be wrapped up on the south side of our building. That new accelerator is going to be 300 of those things. Not all the same size and shape, but all that same kind of design. 300 of those things, each at a cost of about $100,000. Yeah, so it's not cheap business. But the next generation, the best rare isotope research facility, we're going to be that way because of the new accelerator we have invented. We are prototyping and testing, and we're going to build the first ones ever. That's really what's exciting around here, is we're making up our own kind of equipment. And that's where the future is. So this is the near future, being able to do this kind of experiment. But our future as a laboratory really depends on that, and doing a good job building those. Again, come back. Maybe I'll be able to show you the tunnel in 2020. We'll see. One big room. The reason we have one big room, you see that yellow bridge there? That's the crane, bridge crane they call it. Rolls up and down on these orange rails anywhere in this long room and lifts up to 40 tons. That's how you move stuff in this building. We're constantly moving things, so that crane has the run of the building. Oh, you might be able to tell there's a difference in color between that section and this section. That is like 2 months old. We extended this room. Why? Because this linear accelerator right now will get up to 8%. If we make it longer, we can get up to higher energy, supernova energy. You want to study how a supernova works? So we're always adding on. We're always improving the laboratory to do new kinds of experiments. Always, always. Mike, is this different? Yes. It was always be different. Anyway, so this is kind of where the future of the laboratory is. Anyway, any questions in this area? No, you guys are so clear on everything.
We're on top of it.